And of course, once we've actually determined if there's a significant F and then where those group differences are with post hoc tests, we also need to talk about how meaningful is that effect, and of course that is effect size. So in ANOVA, there are a few of them. The first one is eta squared, and that is basically sum of squares between over sum of squares total. So the effect of one particular variable, in this case the categorical variable, over the total variance in the dV. So effect over total variance. Partial eta squared is what we are normally going to report, so that's effect, sum of squares between, divided by, again, itself, sums of squares between plus sums of squares within. So basically the effect over the effect plus unexplained variance. And that's partial eta squared. Omega squared is another statistical technique that adjusts for sample size. And I'm not going to talk about this much yet, but the main reason for omega, and we're going to see that more as we move into more advanced analyses, is when we have multiple categorical variables and multiple outcomes. Omega is going to give us a little bit better of an idea in that kind of a more complex situation, the ANOVA that we're going to be talking about in the next couple of weeks. So I just wanted to kind of give an acknowledgement to what it's doing mathematically. So the effect size in this case is actually a little bit different because we're actually including the sums of squares within on the top of the equation plus an adjustment for the number of conditions in the particular IV that we're looking at divided by the sums of squares total plus mean square within. So again, we're kind of getting to a little bit more of a complex adjustment for a complex situation. So then we're going to talk about the within subjects ANOVA. So properties of within subject ANOVA are very similar to the between subjects ANOVA, except one, units in the categories are now dependent. They're the same people, same participants in different conditions, same participants in different times of observations, or different participants if any attempt has been made to match those participants. So the equation itself mathematically accounts for less error due to individual differences. So mathematically, we're actually accounting for or expecting there to be less noise when we do a within subjects ANOVA because we're not capturing individual differences. There shouldn't be any, or they should be very minor. So there's advantages and disadvantages. It reduces individual differences. It increases power, which is also important to recognize that when we're using the within subjects ANOVA, we want to make sure that it's appropriate that we're using it. We are using a tool that is more likely to find differences. And the reason that it's more likely to find differences is that it is making the assumption that it's the exact same people in every condition. If they are not the same people, we need to be very diligent that we have done everything we can to truly make sure those participants are highly matched. There are carryover effects, and they become problematic. So the order people are exposed to the conditions to, each new condition is going to be basically exposed with the knowledge of the old condition. So since it's the same participants, they're going to be aware of the conditions they've been previously in, and those conditions may still have carryover effects to how they react within the new conditions. Also, time-related threats to validity are possible depending on how you're doing this study. So obviously, if you are doing a conditional within subject study where everyone is exposed to all the various levels of a condition within a very short period of time, this is not going to be a time-related threat to validity. However, if the reason you're using it within subjects ANOVA is to expose people to one condition and then measure their observations over the next 2 weeks, another condition and then 2 more weeks, and another condition and 2 more weeks, there's possibilities of multiple confounds that you're actually picking up that aren't individual differences and aren't necessarily reactions to your independent variable or what you're manipulating, but are simply differences found because time is passing. So let's go through a quick example of within subjects ANOVA. Is there a change in graduate students' optimism over years? So again, I've got multiple graduate students, Jared, Dustin, Sylvia, Robert, Cole, and Albert, and I've measured their optimism year 1, year 2, year 3, and year 4 in a 4-year graduate program. So what I'm looking for is, again, Jared is in all 4 conditions. Now, if I did find a significance here, this would be a very good example that I might be capturing not how optimism changes based on year in graduate school. I may simply be just tracking people's change in optimism as they age. So in this case, I actually run the statistics and I find there is not a change in graduate students' optimism, F3, 27. So again, that first degrees of freedom is the number of conditions minus 1, K minus 1, 4 conditions, therefore 3. And then 27, in this case, it actually is the number of times, not only the number of participants, but the number of times they were measured. And I get an F of 1.2, which is non-significant. So now we're going to move on to the factorial ANOVA. So single factor designs or one-way designs only have a single independent variable, and again, no limit to the number of conditions within that independent variable. Factorial designs have more than one independent variable. Now, it should be noted that again, we can add any number of independent variables in a factorial design, though typically we talk about factorial designs in the terms of two independent variables. Likewise, each independent variable or factor can have multiple levels, two or more, and in this case, we will often find that the simplest factorial design is what's often referred to as a 2-by-2 factorial design, two independent variables, each with two conditions. The reason this is appropriate compared to t-test is we no longer have a single IV, so we can't run a t-test. We have to do the factorial ANOVA. So within that 2-by-2 design, we're going to be testing for multiple effects. We're going to be testing for the main effect of our first IV, factor A. We're going to compare and look at the main effects for our second IV, factor B. So main effects represent simply their isolated impact on our DV. And finally, we're going to look for the unique combination or interaction level of each factor. So is there an interaction between factor A and factor B? So we're going to compare the individual group means of each combination of those two factors to look for differences. Do one factor depend on levels of another? So looking at this from kind of the viewpoint of the ANOVA is a very isolated and specialized version of the multiple regression. So again, multiple regression is our kitchen sink statistical technique. We can do just about anything with it. With a factorial ANOVA, though, it's specifically designed to look at categorical IVs. So basically, if we're thinking of this from the terms of a multiple regression, what a factorial ANOVA 2-by-2 does is it looks for the main effects of the first factor, the main effects of the second factor, and creates the interaction term to look at the interaction between those two variables. So again, we often can kind of visualize this just looking at the factorial ANOVA, and this would be a good example of two main effects but no interaction. So if we look at the difference between upper and lower classmen, we see that regardless of whether you're in psychology or anthropology, one of our IVs, the second IV, whether you're a lower classman or upper classman, is going to be we're basically looking at the scores 0 to 4, GPA in this case. So if we look at lower classmen, we notice that lower classmen, if they're an anthropology major, have lower GPAs than upper classmen. And lower classmen, if they're a psych major, have lower GPAs than upper classmen. We can also see by the graph that in general, psychology majors have higher GPAs than anthropology majors. And finally, as these two lines do not cross, nor would they ever cross, there is no indication whatsoever of potential interaction. This would be an example of an interaction. In this case, we may still have main effects. We may still have a general difference between the success of CBT versus psychodynamic theory. We may still find a general difference between males and females if we looked at the marginal means. However, the lines are clearly crossing, which tells us that there's more of an interaction, and the interaction is what's important. Another thing to remember with factorial ANOVA is that when we do find an interaction, the interaction is what's interesting. In other words, if we find two main effects and no interaction, the main effects are worth talking about. If we find one main effect and no interaction, the main effect is what's interesting to talk about. However, if we find an interaction, the main effects are actually misleading. So for instance, if I found in general that females respond better to therapy, and I reported that main effect, that's not necessarily true. If I reported that in general, CBT therapy was higher or better than psychodynamic theory. Again, that is maybe not completely true. Those would be the main effects from this graph. What's more interesting, though, is that interaction, that there is a large gender difference in CBT. There is not a large difference in psychodynamic theory. So we want to really take a look at what the interaction is and where those significant differences are, and that's what we'd be wanting to report.